Okay, thank you, Mattia. So thanks to the organizers for organizing this meeting, Tamara and Sasha. It's wonderful here to be here as always, and we have some great time this week, I guess. So I want to talk to you about joint work that's still not finished, but we're getting there, with Christophe Charrier, Maurice Duits, and Jonathan Linnell. They're all from KTH in Stockholm. And it's about tilings of a hexagon and the connection with orthogonal polynomials that are orthogonal with non-Hermitian orthogonality on a contour. Okay, so that's what I want to talk to you about. And okay, let's just get started. So we'll talk about tilings of a hexagon, and we already saw some pictures like this week. So it's this hexagon here that you tile with three types of lozenges or rhombi, right, with these three shapes and three colors. And you can also view it as boxes that you put in a corner of your room, right? If you move places, right? You recognize the picture maybe. And so many people have looked at that in many different situations, right? And the most famous result here is that if you put a large random tiling here, just uniformly at random, and you see this curious phenomenon that was called Arctic circle, that near the corners of the hexagon the pattern is sort of fixed. That's the frozen region. And it's separated from this interior region, the liquid region, by a circle. I mean, in the large n limit, this will be a circle with probability 1. So that's a very curious thing. And what's also known is that fluctuations around the corner, around this Arctic circle are given by the Airy process, right? Again, in the large n limit. In particular, if you look at some, say, vertical line here, you see the Tracy-Widom distribution. And inside here you see fluctuations that are governed by the Gaussian free field. So there are many things and many more interesting things going on. So for my purpose, it will be convenient to make such an affine change of coordinates and put my hexagon like this, right? So that we have now three types of tiles, but there is a square tile and then these two other tiles that are some quadrilaterals, right? And here is a typical tiling that you may have. So I'm going to use a non-uniform model, meaning that not all tiles are treated equally. So some tiles have a higher probability than others. So, and you can also play with that, and there are many variations on this theme you can do. So what I will do is the following. I put a weight on a tile. Well, actually, the weight, it's determined by the weight of the square tile, right? And it depends then on the vertical line that this vertical tile is in. So if it's an odd-numbered column that this tile is in, then I give it a weight alpha, which is a parameter in my model, and otherwise it's just weight 1. And my alpha will be less than 1. Okay, so, and then the weight of a tiling will be the product of the weights that I put on these square tiles. Right? And then, as usual, then the probability for a tile is proportional to its weight. Okay. And so it will be a non-uniform model, and so if alpha is 1, the parameter is 1, then we come back to the uniform model where each tiling has weight 1, right? And so they all have the same probability. If my parameter alpha is less than 1, then it means that there is a certain punishment if I put such a square tile in an odd-numbered column. For example, in the first column, if I put there such a square tile, then okay, my probability, or my weight becomes smaller, right? So in particular, if alpha is 0, then I don't want any square tiles in the first column, not in the third column, and so on, right? So then I get this picture, right? I also should emphasize that I'm working here with the regular hexagon. So all sides have length n, same length n. So there's only one possible configuration, one possible tiling which has a non-zero weight if alpha is 0, right? And so you see this pattern that because in this model after this transformation of coordinates, it just means that you have to put all, you cannot put any square tiles in the first column. It means that you have to put all tiles like this. The red tiles should go in the first column, all of them, and then you have this square tile, and then it alternates, right? And the other tiles are here. And so you can view this as a sort of a wall, right? It's very much in the news today, these days, the wall. You have the bottom here and the ceiling, right? And so it's a wall, but not very smooth wall, right? So, okay, so that's the case when alpha is 0. That's only one, so the ground state is only state that's allowed. If we take a small alpha, so then, okay, we can allow for this square tile in an odd-numbered column, but not too much, right? Because otherwise the probability will be very low. But then you see a picture like this. If you grow the size of your hexagons, so there is near the boundary between the floor and this wall, and also between the ceiling and the wall, there is some liquid region coming in. I mean, the randomness starts happening here and down here. And so you have two disjoint regions where there is this, we have a non-trivial phenomenon here. And these turn out to become, in the large n limit, there will be two ellipses. They are tangent to the sides of the hexagon. And in between, there's a frozen region, but this frozen region is sort of special in the sense that it consists of two tiles, right? Usually here on top and the bottom, for example, you have only one tile, one possible tile in the frozen region. Here you have a frozen region consisting of 2 out of the 3 possible tiles, right? And it goes from left to right here. Then if you increase your parameter alpha further, it's still less than 1, but it's not a tiny alpha anymore. Then what happens at that these two ellipses in the limit will come together, they merge, and in the large n limit you see a liquid region that's bounded by a more complicated algebraic curve. And so that's what happens, and you can also see that there's still this special frozen region where you have two tiles, up here and also over here, but it's no longer going all the way from left to right. So this is also broken, right? So this is the kind of phenomenon that we see from these computer experiments and that we want to analyze and see what happens. In particular, this transition from two ellipses, they become tangent at some critical alpha and then merge to form this picture. Okay, so there is a way to look at this from non-intersecting paths, right? Which is very well known to people who work on this, but still, let me explain. Not everybody may have seen this. So, given a tiling here, okay, I use other kind of colors, but you can put some lines on each of the possible tilings. Well, actually only the square tiles have a horizontal line on them, and the red ones here that go up, they have also a line along the diagonal. And these lines then combine to form paths. That if you have an n by n hexagon, there will be n paths here starting on the left. They can go either horizontal or they can go diagonally up. And they end here at these, over here, they're sort of fixed positions. And they are non-intersecting. Okay, they cannot cross each other. And you can convince yourself from the fact that once you have such a system of these paths going like with these initial positions and also given ending positions, and they cannot intersect, that this is in one-to-one correspondence with a tiling of this hexagon. Right? So that so you can also view it in terms of these paths. And these paths you can then also put on a graph. Here is an example, and so you also have. So this graph is on the integers. The integers are the z2. That's the set of the vertices, and you have edges going horizontal or diagonally up. And it's a directed graph, right? So you should follow the direction, and again, you can put these paths on this graph with prescribed starting positions here, which are consecutive here at some level 0, and they should end here at level 12. In this case, it will be 2 times n. Well, n is the size of your hexagon, right? And again, it's a one-to-one correspondence. You can put also particles on these paths and think about some interacting particle system here. So I can also now put my probabilities on the graph, right? So that's what I will do. So if you you give each edge a weight, depending on where it is in the graph. Actually, most edges will have weight 1, right? Except there's a weight alpha if the edge is a horizontal edge in an odd-numbered column, right? That exactly then corresponds to the tiles that are the square tiles in again an odd-numbered column. So that's the weight of an edge, and if you then have a system of these such paths that are non-intersecting, and here's such a path system, P1 to Pn, then the weight of such a path system is just the product over all edges that are covered by all these paths, right? And then again, the probability of a path system is proportional to its weight. If you put it like this, view it from this, you can use well-known results due to Lindström and Guess-Viennot to see that such a system of paths of particle system becomes determinantal. Right? That is a very general fact. You can express the probabilities to be that your paths are at a certain set of locations at some intermediate level in terms of a product of two determinants. And it will also involve this alpha. And so then there's also formalism. Oh yeah, this is then this, this comes out of this Lindström-Guess-Viennot considerations, that if you have these particles, or these are just the positions of the paths at a certain level m here, m is the level, j is the jth path, counting from bottom to top. This probability is equal to such a product of determinants. Okay, so it's quite a complicated formula, but what is important here is that there are certain matrices coming in that sort of describe some transition matrices from level m to actually from level m minus 1 to level m. How to go from one level to the next. And this is given by such a transition matrix or transfer matrix, which is very simple in our case because we can only go either horizontal or we can go up. It means that if we go horizontal with a certain weight, it is alpha or 1, right? That depends on whether we are at an odd or even m. And if I can also go horizontally up, so if we go from, if y is x plus 1, we go 1 up. And there's a weight 1, so that comes into this transition matrix as a 1 here. And otherwise, you get zeros. So I like to think about this as a matrix over the integers. So x and y are both integers. So it stretches out in both directions to infinity, this matrix. And on the diagonal, we have alternating alpha and 1. No, not alternating, depending on if m is odd or even, we have this parameter alpha or 1. So it's either alpha on the diagonal or 1. And it's a 1 on the first upper diagonal, and otherwise it's 0. Now, such product of determinants is quite common in random matrix theory and other related processes, and it's known that this will be a determinantal point process. And there's a general formula here, formalism, going back to Bertrand Einard, right, who may be here, and Madame Mehta, that will give a formula for this correlation kernel in quite generality, right? And there will be a sum formula, a double sum formula, and also a single sum. But here, the special situation is that these matrices they're constant along the diagonal. Right? They're tuplets matrices, infinite tuplets matrices, and so with some but earlier work with Maurice Duits, we considered such a situation. And we found other formulas, right? Well, from the Einar Mehta formula, we found integral formulas, which I will present in a minute. So here we have these two infinite tuplets matrices, and you have a symbol that's associated with such a tuplets matrix that is just in our case, it's just a simple linear polynomial. So if m is odd, you have z plus alpha. So it's alpha because it's alpha on the diagonal, and it's 1 on the first up. On the next diagonal, that's where the z comes from, and the rest is 0. And if m is even, you have z plus 1. So you alternate between these two tuplets matrices with these symbols. And then our formula for the correlation kernel takes this form. And so, okay, so that looks pretty horrible, right? So let's, now I have to take you through it. But let me first emphasize that this is a scalar version of a more general result we actually have, which is a matrix version of this, which deals with the situation where the matrices are block tuplets. So if they're block tuplets, then we have an extension of this formula. Well, it's actually pretty similar, but instead of scalar symbols, we have also a matrix-valued symbols then, and there's a correlation kernel then in terms of those things that we have, the matrix version. And that we used in our previous work to study the Aztec diamond, tilings of an Aztec diamond that have a so-called two-periodic Aztec diamond, where there's a periodicity in the tilings in both directions. So here we have periodicity in the weighting of the Aztec diamond, which is periodic in one direction. If you put also periodicity in the other direction, you could use this formalism in the matrix setting, right? Okay, so let's look at what we have here. So this is the kernel, x1 and y1 and x2 and y2. So x, y are just coordinates in z times z, right? So both integers that sort of correspond to the positions that we are in the hexagon. So it depends on two such coordinates. And the main thing here is this double contour integral. Okay, so it's this gamma is some contour going around 0. So unit circle you can take, or you can deform it because everything is analytic, except there are poles, there's a pole at 0 for both z and w. Then you have a product of these symbols. Here, so the x-coordinate is horizontal coordinate, so you take a product of the symbols going from basically x2 up to capital N. Capital N is, it should be maybe 2n here, sorry about that. It should be a 2n because, yeah, we go from 0 to 2n. Of all these symbols. That's sort of...
So what are the AMs? Are they square roots?
No, the AMs are these simple linear expressions. And here, the similar factor in the other variable z going from 1 to x1, the other horizontal coordinate, product of all these. But this is just a simple polynomial, right, in our case. Z plus 1 times a certain exponent and z plus alpha, certain exponent. Okay, and then there is, the main character here is this Rn. That's a two-variable polynomial in both w and z, and it's a reproducing kernel for orthogonal polynomials. But orthogonal polynomials on the curve gamma, which could be the unit circle, with a weight that's again formed of, as a product of all these symbols. If you go from left to right, here you go all the way from left to right. You take a product of all the symbols that come with these tuplets matrices, and you divide by z to the 2n. So in our particular case, this just comes out as since we have 2n steps, right? N times we take the z plus 1, and n times we take z plus alpha. So this will be a weight function which is complex valued, right? We're on the plane, in the complex plane, on a circle, and we're dealing now with orthogonal polynomials with this weight. So what does it actually mean? So I take polynomials p little n, so little n is the degree of this polynomial, that should be orthogonal with respect to this weight, orthogonal with respect to lower degree polynomials, right? And so I integrate over this gamma, Pn times z to the k, and k is less than little n, times the weight. Such integral should be 0 if k runs from 0 to n minus 1, and of course, if, I meant to say here, if k is n, then you get some non-zero number here. Now this is unusual orthogonality. I call it, people in approximation theory, where this concept also appears already some decades ago, they call it non-Hermitian orthogonality. Notice that there is no complex conjugation anywhere, right? We're dealing with things in the plane, but there's no complex conjugation anywhere. So actually there's no L2 in a product behind this. This is just a system of linear equations that you could set up to determine the coefficients of this polynomial. But a priori there's no guarantee that there is a unique solution, right? So that's part of the issue actually, that we have to prove existence and uniqueness of these polynomials. But here again, the Lindström-Gesell-Vienno picture helps us, although I will not go into that. In this case here, these polynomials, they uniquely exist for degrees little n going from 0 up to, actually, you can go all the way up to 2 times capital N. Okay, so once you have these polynomials, and we assume that they are monic, leading coefficient 1, then you can construct this reproducing kernel, right? Where you have the sum of these polynomials in the variable w, and then also in the variable z, you divide by this constant kappa n, right? The sort of the square root of the L2 norm in some sense, but there's no L2 theory here. But still, this sum you can set up. And that's the reproducing kernel that I was talking about, that appeared here in this, formula. Okay, I will go back to this reproducing kernel in a minute. I should also point out that there is another term here in this correlation kernel, which actually is only there if x1 is bigger than x2. That is a single integral, which is sort of simpler. Yeah. And it corresponds in our meta formalism to they have a double sum plus a single sum, which is also only there if one coordinate is bigger than the other one. Okay, so this reproducing kernel, there's a Christophe Darboux formula for it, just as with orthogonal polynomials on the real line, that you can express this in terms of the orthogonal polynomials of degree capital N and capital N minus 1. Okay, it's also maybe nice to point out that if your parameter alpha is 1, then this is just, the weight is just c plus 1 to some power 2 times n. Then things simplify quite a bit actually. And then you can express, well, these polynomials Pn actually are classical orthogonal polynomials, namely Jacobi polynomials. They come out as Jacobi polynomials, except that there's an unusual feature here, that one of the parameters is negative, large and very negative. So typically you have alpha beta as parameters in your Jacobi polynomial, and alpha beta are bigger than minus 1. But here there is a large negative parameter here. So that's an unusual thing. But still it simplifies in the case alpha is 1. For the uniform model, it would simplify in that sense. Okay, so that's anyway our starting point for our analysis. We have this correlation kernel, and we want to do asymptotics here where capital N gets large, right? And we also want to scale x and y, both x and y coordinates, proportional with capital N, and see if something can come out of such an integral. It's a sort of, in a way, a two-step procedure. We analyze these orthogonal polynomials on this contour, and that the result of that is, comes, and how does it work out for the reproducing kernel, and then we should do a steepest descendant analysis, say, of this double contour integral, which is the main character in the formula. Right? So in particular, if we just focus on, which I will do for this talk, and we also do it in our paper, focus on the kernel on the diagonal, so x1 is x2, y1 is y2, then it's just a probability to have no paths at that location. And since the paths associated with the two of the tiles, 1 minus the kernel on the diagonal is the probability for this tile, having this tile at that location. This will become an integral where we put x1, x2 the same. Let them be x, and y1 and y2 are y. And we have our formula from the previous slide becomes this one. So we want to analyze this in the large n limit to see what happens. And in particular to identify these two ellipses, right? If alpha is small, and the more complicated contour if alpha gets bigger. How to see this phase transition coming up here. There are similar double contour integral formulas for the other types of probabilities, right? For the other two tiles. Okay, so this is the large n limit indeed, as I was already hinting at. We want to increase capital N, and then both x and y, the two coordinates, would scale with capital N, so that we focus on a fixed point on our hexagon. And I took coordinates in the hexagon like this. right? So that both psi and eta, the limiting coordinates, are between -1 and 1. And 0, 0 is in the center here of the hexagon. You see here the corner points. So what we can compute is a so-called saddle point for the double contour integral, which will depend on psi and eta. Right? And as is maybe somewhat usual thing in these kind of models, there will be a number of saddle points, but there will be a relevant saddle point which is either in the complex plane, in the upper half plane, or not, right? And the liquid region will then be characterized by the fact that the saddle point is indeed in the upper half plane. There will be a corresponding saddle point also in the lower half plane. And the frozen region will be characterized by the fact that all these saddle points are real. So how do we get to these saddle points and a saddle point equation?
Arno?
Yeah?
All the other saddle points are real and you only have two complex conjugate ones?
At most, yes. Yeah.
Okay.
Yeah, we'll come to that. So, yeah, so then we have this kind of picture. Then our result on the limiting probabilities for these two tiles, we still see so this is in the liquid phase. Once we're in the liquid phase, we still see the periodicity with alpha going from left to right, even odd case. And we can nicely express them in terms of angles of two triangles. So if we put in the complex plane, put a vertex at 0, at -1 at the saddle point that varies with the coordinates, we have a triangle with three angles, and we can also put the triangle here, but the difference is that this corner point is minus alpha instead of -1, and we have another triangle with different angles, and the limiting probabilities to find the tiles of these different possible tilings, these limiting probabilities, they have limits, and they're given by these angles divided by pi, right? So this angle, of course, is the same here at 0. That corresponds to the probability to have a tile of this form at a certain location. That will have a limit, which is related to the argument of this saddle point. For the other two tiles, the angles are different with alpha or not. And then we have different limits depending on whether it's x goes to even numbers or odd numbers. Right? So this is sort of a neat way to describe these tiling probabilities.
Arno, sorry, I missed that. Where are you scaling inside the hexagon for this one?
So psi, eta are limiting coordinates. So x is proportional to 1 plus psi times n. Right? So if
Dennis, where is that in the hexagon?
So psi is the horizontal coordinate for the hexagon, and eta vertical. So you can take any point here inside the hexagon, right? That's why it has coordinates psi and eta. I haven't told you how the saddle point depends on psi and eta, but if it turns out to be in the liquid phase, that its imaginary part is positive, right? That it will depend on where you are in the hexagon. Then if you let x and y increase with n in this way, right, that these limits hold true, then you find these limiting probabilities for the probabilities to have a certain tile at a location x, y. Right? Okay. So let me tell you how we find these saddle points and what is the saddle point equation. So we first have to go through analysis of these orthogonal polynomials. We will do Riemann-Hilbert analysis for that, but not yet. Oh. It will turn out that these polynomials, if we let capital N grow, and we have to also remember that capital N is now the degree of the polynomial, but the orthogonality weight also varies with capital N, right? So its orthogonality with respect to varying weights as well, but it will grow so there's a function g depending on z, and our polynomial would roughly grow like this if capital N gets large, or grow or decay, it can decay as well. It will also then mean that this reproducing kernel approximately and grows like this. It's a rough idea here that this is not quite true, but for the idea that this is good enough. So if you make this approximation here for Rn in the integrand of the double integral, and you look at where all these x's and y's are in these, let's scroll back here, right? And you write these x as 1 plus psi times capital N, right, to have a first approximation, and y similarly in terms of eta, then you find that the integrand there is roughly like this. You have these, the behavior in z is in here, and then w is here, and I put everything to the power capital N, right? So if you put everything under inside an exponential, this z plus 1, z plus alpha, etc. become logarithms, and that will be then your action functional, depending on the coordinate psi and eta then. And the saddle points will then be the derivative, it will be zeros of the derivative of this function of z that you get. So you get some expression from here in the z variable like this. This will come out. This is the saddle point equation, say for saddles coming from this one. And here it's slightly different. The pluses and minuses are somewhat located at different positions. So there's, together with this one, these are the two saddle point equations. Okay? So that's sort of, but we still need to get our hands on this function g. So what is the function g? That comes from the asymptotic behavior of the orthogonal polynomials when n gets large. So how is this g function related to the orthogonal polynomials? So it will come typically from the zeros of the polynomials. So if you have polynomials now with degree n, it has n zeros in the complex plane. You put a mass 1 over capital N at each of the zeros. This is an empirical measure then for the normalized counting measure of the zeros. This will have some weak limit. Right? Let's call it mu 0. And then this g function will be the logarithmic transform of this limiting counting measure. That's what we should be using. So that leads to the question, where are the zeros actually? Right? Because we're dealing with complex orthogonality, the zeros are in the complex plane. Huh? And indeed they are. And for the case alpha is 1, since these are just Jacobi polynomials but with unusual parameters, but this has been studied before by Martinez, Finkelstein, Orive, also related work by Driver and Duren. And it turns out that the zeros here, they will cluster to an arc on the unit circle. Okay, nice. If alpha is less than 1, but still not too small, the zeros we can calculate, well, numerically we can calculate, and we can also prove it, that the zeros will cluster to an arc on a circle of radius square root alpha. And if alpha goes to this value 1 over 9, this circular arc will close up. And 1 over 9 is actually the critical value for this behavior of zeros, but also for this model, for the tiling model. If alpha is 1 over 9, below 1 over 9 you have these two disjoint ellipses. So alpha is 1 over 9 is the critical value, but you see it also already in the zeros of the polynomials. So here, well, you may say, well, why is this closing up? Actually, the density of zeros at this point here, -1/3, is very low. So I have a large number of zeros, but not large enough to really see that, indeed, in the limit, this will close up. Right? You have to believe me there. The density of zeros is very low. Here it vanishes quadratically. And if you do local analysis at these, for these polynomials at this point where the zeros close up, you would have to use some Lex-pair solutions associated with Hastings-MacLeod solution of Painlevé II. So that has to do with this two tangent ellipses in the model of these tilings. Okay, so now there are techniques developed to calculate this G function in cases of non-Hermitian orthogonality. And that was developed by Herbert Stahl already in the 80s, and from the point of view of in relation to Paret approximation, where you also have non-Hermitian orthogonality, and he came up with this concept that in our case we have a varying weight situation, and there is a V that has this combination of logarithms. It comes from our weight function. We take a logarithm there and divide by minus n. This is what we have. And this G function should come from this measure, mu0, that we have to determine. And it should be such that it should be located on a contour around 0. And the real part of this combination, so you have this G plus G minus, these are boundary values of G on the contour, where this G function will have a discontinuity, minus this external field V, plus a constant. This real part should be 0 on the support and less than 0 on the rest of this contour. These are actually the usual equilibrium conditions that are associated with equilibrium measures and external fields that maybe some of you have worked with or read about. What is typically here for problems in the complex plane, that you, on the curves, the complex plane, that you also want to condition on the imaginary part. So the imaginary part of this same combination here should be constant on each component in the support of the measure. So for us, we have only an arc or a full circle, so this is just one component. So the imaginary part should also be constant. Okay? This property is known as the S property, or symmetry property, or property of Stahl. That is part of the problem. We have to find a curve with the S property in its external field V. Now, what comes out here is that if you take a derivative of these relations, you will see that the derivative, the sum of the derivatives of the G function, the boundary values on from the two sides on the contour, is equal to the V prime on the support. If you play with that, you will see that this is actually G prime, this Cauchy transform of your measure. This is G prime. G prime minus V prime over 2 will have the property that its limiting value from the left and the right, they just change, they differ by a sign only. That comes out from this, which means that if you square the thing, it becomes continuous, and in particular analytic. So this function here will be an analytic across the contour. That's very special. And so its singularities are only the singularities of V prime. And V prime is this combination of logarithms, and we take a square, so this Q alpha will come out here as a rational function, which has double poles at the singularities of V, which are of V prime, which is 0 alpha and or minus alpha and minus 1. And so we are able to calculate this Q alpha. Okay? And we see the transition at the number 1/9. If alpha is bigger than 1/9, then this Q alpha, well, it has double poles, as I already indicated. It has two simple zeros, at z plus and z minus. This will be the endpoints of this limiting support of the zeros. Z plus in the upper half plane, z minus in the lower half plane. And there is in addition a double zero here at minus square root alpha. If alpha is less than 1/9, then you still have these double zeros, double poles, but then you have double zeros for Q alpha. So at the value of alpha is 1/9, these two simple zeros, z plus and z minus, will come to the real line at the value minus square root alpha. Exactly on top of this double zero that you also have there. So that will create a quadruple zero at this critical parameter. And then if alpha decreases further, the degree 4 zero will split into two double zeros. Like this. Okay, and then these two saddle point equations, if you combine them, square them, they become one equation, and that can be written then in terms of this Q alpha. And Q alpha is a rational expression. This is also rational with the same double poles. And so if you clear denominators, you will see that you get a degree 4 polynomial equation in Z. And that's the saddle point equation that you come up with. So there will be 4 saddles for every choice of psi and eta. And so we can prove that if psi and eta are coordinates so that we are in the hexagon, then there are at least 2 saddles in this interval from -1 to minus alpha. And hence there can be at most 2 non-real saddles, and because of symmetry in the real axis, there can be at most 1 saddle in the upper half plane and at most 1 saddle in the lower half plane. And so that determines the liquid and the frozen regions. The liquid region is the region, psi eta coordinates, for which you have this saddle in the upper half plane, and otherwise it's frozen. Okay, so that comes out of, okay, I have 3 minutes, I can show you pictures. This is then what we can calculate, this polynomial equation. We can see where it has double zeros, right? And that's the boundary of these liquid phases. We have at alpha, for alpha bigger, these 2 ellipses become tangent. And at the critical value, alpha is 1/9, we have 2 tangent ellipses and then we have a tacnode. Okay, so I have a Riemann-Hilbert problem, but I only have 3 minutes. So those of you that can read fast, read with me, yeah? Maybe Dived, Krieghaber, McLaughlin, Vinnicky, so you should read all these names, right? They developed this technique to get information, large n information from this Riemann-Hilbert problem. It's in the same way as in the case of orthogonal polynomials on the real line, more or less. Then the steepest descent analysis of the contours is still quite some business. And that actually took us, and it still takes us quite some headaches to get it, but we need control of certain contours. So once we have, we focus on some point in the liquid phase, we have a saddle in the upper half plane, and its complex conjugate is the other saddle. And so there's a certain function phi for which this is a saddle, for which the derivative is 0 at the saddle. And there are level lines then of this function phi that we have to control. And this is a typical picture. The red line here, this is the circle of radius root alpha. These are the level lines, critical level lines of this phase function, and we need good control of that. And then we can deform contours. We have nice pictures, but even nicer picture, and then we get our results. So, okay. My time is up. So there's a paper coming out soon. I've been saying this for at least half a year, but okay. And this is the other paper that we rely on with Maurice, which, and let me thank my sponsors, and also I want to make use of this opportunity to advertise that there is a postdoc position at KU Leuven coming up soon, almost sure. So thank you for your attention.
Thank you, Arno, for your talk. And now is questions. Done.
I have a...
Wait. Yeah, but it's
Am I missing something here when I say that? So in Pierre's talk, the cusps were sort of in the time direction, whereas in your case, the cusps are perpendicular to the natural time direction. Is that?
Yeah, I mean this cusp here in the.
And the time direction in your case is the x is vertical.
Yeah, I think about this as time. Yeah, then. Yeah, sure. Yeah, you have two groups of paths that can be separated, or they can be in the time-like direction if you wish. Yeah, yeah.
Does that mean the behavior is different, or?
At the cusp. No, I
there's
think
a 90
this will
degree
be the usual PRC limits you find there. I'm pretty sure. Maybe you're right in the sense that this periodicity 1 and alpha you also see here, but okay, I haven't thought about that. If you still see some variation there that I'm not sure about.
any other question? Okay.
Yeah.
It's background information. So the fluctuation of the boundary in this region. Oh, you could leave it on that previous picture that you had.
In the.
I mean, I'm just making sure I understand. Your determinantal representation lets you prove derive the fluctuations of the boundaries in all of these frozen regions, at the boundary of all frozen regions.
We're not focusing on that because there's plenty to think. We thought about thinking about focusing on the tile probabilities, right, in the liquid region, but we could also focus on the boundary here and find the area behavior and the area process.
You also can get the area process and this doubly periodic region.
Okay, that again, I'm not sure. If the alpha is still there, that may be an interesting thing to look at, to see if there's this alpha is still visible here in the fluctuations on the boundary. Yeah, that's a good point. Yeah.
Any other question? I actually have one. So you said that you are in the scalar case here. You have scalar turquoise determinants because you have periodicity just on one side.
Yeah.
So do you expect some gas phase to emerge if you do?
Yeah, good question. If we also introduce periodicity in our weighting of our tiles in the other direction, then you need to go to at least 3 periodicity to create a gas phase in this hexagon model. You have to create a situation, the spectral curve should come from a higher genus, have a higher genus. And that can only be done if it is at least 3 periodic, yeah. But indeed, that's what would be very interesting to do, and we're working on it, yeah. Okay. But, Sasha.
Actually, sorry to follow up on your question. So you explained in the Riemann-Hilbert problem you have real roots and complex roots, and in gas phase, how would you expect it to express itself on the level of the Riemann-Hilbert problem?
Well, this cell point equation doesn't come, it comes from the G function essentially, which in the gas phase, I know how it works out in the Aztec diamond, so let me do that. We have, there are, like, you have a situation where you have bands at 0 and at 2 negative. It's a hyperelliptic curve which branches at infinity, 0 and 2 negative points. And it depends on where the saddles go. If they go in the gap between the 2 bands or not. And they can, if all 4 saddle points are in this a gap, then you're in the gas phase in that model.
Any other question? If not, let's thank Arno again.
Thank you.